Overcurrent and earth fault protection, the workhorse of distribution protection. This is a full study workspace for it, staged phase and earth elements, time current curves, and a live directional model built on real relay behavior. Pick your reference relay: Schneider MiCOM, Siemens SIPROTEC, SEL, or as we're set up here, an ABB Relion 615. Each profile carries the behavior documented in the vendor's own manual. First, the time side. Pick a curve, IEC standard inverse, set the pickup and the time multiplier, and the tool plots the full time current curve. At 10 times pickup with a TMS of 0.1, standard inverse operates in about 0.3 seconds. Very inverse and extremely inverse change the shape, and the ANSI curve family is in here too. Same IEC maths every relay uses. And every change lands in the interpreted results. The verdict at the top, the operations summary below it, and the expected operate window 0.28 to 0.31 seconds with the timing tolerance applied. Now make it directional. The element gets an operate sector, a range of angles around its characteristic. On this ABB profile, a characteristic angle of 30 degrees puts the operate center at 60 degrees, with the sector shaded either side of it. Put the test phaser inside that sector and the element is permissive, it will operate. Now flip the element to reverse. The whole sector rotates 180 degrees, center to 240. The same test phaser is now outside, directionally blocked. That flip is the entire point of 67. The characteristic angle, the RCA, points the sector at where the fault current actually sits, relative to the polarizing voltage. On a solidly earthed system, a phase fault lags by something like 45 to 70 degrees, so you align the RCA to catch it with margin. Rotate it, and the sector swings with it. The goal: the fault phaser sitting comfortably mid-sector, not near an edge. Here's the scenario that catches people out. The relay loses its polarizing voltage, a blown VT fuse or a close-up three-phase fault collapsing the voltage. The directional element has no reference. What happens next depends entirely on what you set. Drop the voltage below the threshold with everything switched off, and it's blocked. No voltage, no decision. Turn on voltage memory and it rides through on the remembered pre-fault voltage for as long as the memory timer allows. Or allow non-directional operation and it falls back to a plain overcurrent trip. One catch the tool makes visible, polarize on negative sequence voltage, and voltage memory is suppressed. That same low voltage case goes straight to blocked. Knowing which of these your scheme does is the difference between a correct trip and a missed one. Last, earth faults on compensated or isolated networks, Peterson coil systems. The residual current is tiny, and the angle barely moves. A normal directional element struggles. That's why these relays have special families. Wattmetric looks at residual power and narrows its sector, on MiCOM to plus or minus 85 degrees once the power threshold is armed. Icosφ and Isinφ resolve the residual current onto the active or reactive axis, and Siemens does the same with its real power and reactive power earth elements. The tool shows each as a live comparator, not a label. To be clear about scope, this is a modeled manual-backed study and interpretation workspace, not relay firmware and not configuration software. That's exactly what makes it a strong training tool. Every behavior you just saw is live calculation on screen, not a slide deck. So whether you're checking a directional decision, grading a feeder, or teaching 67 to a junior engineer across MiCOM, ABB, Siemens, and SEL, The link is in the description. Run your own studies and put it to the test yourself at eiportal.com.